So let's go ahead and take a look here at example number 3 to actually try to prove that this sequence here does indeed have a limit of 1. Now again, I can think about what this means in terms of my picture. Again, if you're going to say the limit's 1, that means you're going to say that each of these black dots will continually and endlessly get closer and closer and closer to the value of 1. So if that's the case, then that would mean that eventually the green gap should be smaller than any number I claim. So I'm going to start here just with a little bit of scratch work to try to understand the idea. Here's some scratch work. Let's suppose, just for the sake of argument, that I want to know how far down the list do I have to go before these gaps start getting smaller than, I don't know, how about we say 1/1000th? I'll even write that as a question. How far down the list must we go to get, let's see, values of the sequence that are within 1/1000th of 1. Notice that when I talk about these values of the sequence being within 1/1000th of 1, I am talking about the green gap, right? I'm talking about that green gap being less than 1/1000th. Well, that's kind of a difficult question to answer in general, right? I mean, because that would depend on maybe how complicated this limit is to try to start figuring out when do these gaps get small enough. But notice this is something I can actually solve for algebraically very simply. Let's start to measure one of these green gaps. Notice to get one of those green gaps, I would have to do my a sub n minus my L. Well, since I don't know what dot I'm looking at yet, I'm just going to use this general formula for a dot. And I know that my proposed L is the number 1. Now I want to simplify this because I want to figure out when might this come out less than 1/1000th. When do I actually, or for what values of n can I plug in that this becomes less than that? Well, let's see. Maybe to simplify this, I'll start by getting a common denominator. So I'll have an n plus 1 over an n plus 1. Now, of course, if I subtract here, don't forget I have to subtract the n and the 1 in the numerator. So I'm going to be left with a negative 1 over n plus 1. That, of course, when absolute valued, is just going to be 1 over n plus 1. Notice that the top is now positive and the bottom's positive, so this is my result. So notice that what I have right here is a green-sized gap. That's a formula for it. So if I plug in the number 1, I know that my a sub n, my dot, and my L at spot 1 are going to be 1/2 apart. Well, that makes perfect sense, because remember up here in the picture, my first dot was at a height of 1/2, so it's 1/2 away from the line. So this is a formula that just helps to measure those green gaps. And our goal is to ask, we want to know when 1 over n plus 1 will be less than 1/1000th. Well, this actually then seems like a very, very reasonable and easy question to answer. Notice by multiplying both sides by 1,000 and multiplying both sides by n plus 1, I end up with this. And then to solve for n, I'm going to end up with n has to be greater than 99. Oops, sorry, not 99, 999. Forgot a 9 there. But that tells me that ultimately, if I go over 999, notice that means that 999 is my blue value of capital N. That's what I have right here. Then once I go past that, I should be able to see a gap that is small enough. Now, I can easily double check that. Notice if I plug in 999 into my sequence, I'm going to get 999 over 1,000. How far away is that from 1? Oh, it's 1/1000th. So if I want to get under a gap of 1/1000th, I just probably have to go past that spot. Now, of course, we haven't proven that the limit is 1 yet. We just showed that we can get a gap of a green gap here that's smaller than 1/1000th. But we don't want to just show that we can get a green gap that's smaller than 1/1000th, because you have to convince me that the gaps get as small as I could ever want. So how about we try to redo this argument with the idea of an arbitrary epsilon. So I'm going to go ahead and repose the question. I'll say, how far down the list must we go to get values of the sequence that are within epsilon of 1? What if instead of saying that the size that I want is 1/1000th, what if I just said it's epsilon, like it's a placeholder value? I don't know exactly what size gap I'm trying to beat just yet, so let's just use a placeholder. Now notice I can do all the same work in pretty much the same way. I can start by saying, let's calculate the size of a green gap. I know exactly how that's going to work. I plug in all my stuff. I'll even skip some of the simplifying. And I know I get down to 1 over n plus 1. That's still the size of a green gap. But now I can think about what it is that I really want with this. So we want the size of our green gap to be smaller than not just 1/1000th, but really any number that anyone would ever tell us. Smaller than epsilon then, whatever that epsilon happens to be. Notice I can still go ahead here and attempt to solve for the value of n. Notice if I multiply both sides by n plus 1 and divide both sides by an epsilon, I can end up with the following. 1 over epsilon is less than n plus 1. And so I can say that n should be greater than 1 over epsilon minus 1. Notice that this tells me again right here a big blue value of n. But here's the benefit. We were able to establish this now. What we established again was that our green gap could be as small as we wanted here, really, right? Smaller than any number, as long as we looked past this value in the list. Notice then, if my epsilon was 1/1000th, I would have to look past 1 over 1/1000th, which is 1,000, minus 1, 999. It generates that value. But what if I wanted to be less than, I don't know, say a billion, right? Or, sorry, 1/1 billionth. Well, then that's pretty easy, because I would say, well, then how far down the list do I have to go to start seeing green gaps getting that small? Well, I have to go 1 over 1/1 billionth, which is a billion, minus 1. So that's 999,999,999. Right? Like, this is a formula that tells me exactly how far down the list to go. And so I can go ahead and I could write something like the following. Oops. I can say, so if we go past n equaling 1 over epsilon minus 1, then the absolute value of a sub n minus L will be less than this for all epsilon greater than 0. That gives us exactly what we wanted, and that allows us to say that the limit as n approaches infinity of a sub n is going to be equal to 1. Now, I've left off a little bit of the detail here in terms of writing out these last statements and carefully showing this, but I'm going to, since this is not going to be a major focus for us here in Chapter 5, I'm going to leave those details for the notes up in Blackboard. But hopefully this gives you at least a loose gist of kind of what it is that we're saying when we have a limit here equaling a value of 1. Now, before we go ahead and move into some other examples, we can quickly go ahead down here and define one final thing. What does it mean to have a limit of a sub n that equals maybe infinity? Well, this means that for every positive number m, there is an integer capital N such that if little n is greater than big N, we would have a sub n is greater than m. Again, all this stuff sounds super confusing when we try to think about it in this way, but I'll go ahead and just try to think about it graphically. First off, I could easily see that if I had a sequence that was going to be going off to infinity, that would mean that the numbers in my list just like keep getting bigger and bigger and bigger, right? Like they just constantly are going upward. But if they constantly go upward always, then don't you eventually have to get a dot that's bigger than, say, 1,000? Don't you eventually have to get a dot that's higher up than 1,000,000? Or 1,000,000,000,000? Or 1,000,000,000,000 to the trillionth power? Don't you eventually have to get a dot that's higher than every single possible positive number? Like you can always find dots that meet that criteria? So what we're doing here is we're saying this value of m is going to kind of act as like a threshold that I want to say, can I ever get dots above this? I should be able to if this limit goes off to infinity. And so again, our value of capital N says, yeah, once you get past a certain point, you can see that you start to get dots above. Our goal would be to show that for every possible red line that we could ever draw, for every possible value of m, I'm always able to go far enough down the list to get something larger. These dots should always continue to grow in size. A similar definition can be formed for when we have limits that approach negative infinity. Now what we'll see in the next videos is some of the consequences that come from these complicated starting definitions. And these consequences are ultimately going to allow us to compute some of these limits in much simpler ways than what we actually can start with here on the base definition.